Good afternoon, everyone. My name is Alexandre Gouveia, not Fulgêncio. I am from R&D Nestor, which is a research company co-owned by the Portuguese TSO. And I'm presenting the paper titled System-Wide Nodal Capacity Allocation Applied to a Spanish Distribution Network. This work was developed in the context of a Horizon 2020 project called Interpreter, and it was made in collaboration with a Spanish TSO called CUERVA and the Spanish Research Center Fundación CIRCE. And these are not the only partners from the project, but these are the ones that participated in this project. So, starting with a brief introduction and motivation for this work, as we all know, as there are an ever-increasing demand and ever-increasing push for decarbonizing the economy, there's an increase in integration of renewable energy resources, especially at the distribution level, which will make grid operators to face new challenges that they weren't used to facing. And unlike transmission networks, there are no centralized guidelines for grid reinforcements in the distribution side, and there's not much transparency with regards to nodal capacity allocation approaches used by DSOs. In nodal capacity allocation, I mean, when installing what is the capability of grid nodes to absorb new power injection? For instance, in the installation of a distributed energy resource. In the literature review, we noticed that this problem, the MCA problem, has only been partially addressed, either with already predetermined amounts of power that need to be distributed across the grid, or already predetermined positions, which would then need to calculate the maximum power injection level. And there's little application of this problem to the distribution level, which will need to be addressed. And it was addressed in our proposed solution, which was a tool which aimed at maximizing distribution generation absorption at the system level, so with no predefined location, for new generating nodes. So we want to maximize total power injection. It is capable of advancing distribution networks. It is generation technology agnostic, so it doesn't care which technology the energy source is. And it is capable of providing an analysis for system operators, which gives probabilistic boundaries for new DG allocation. So it doesn't give only one possible solution or one optimal solution. It gives a set of solutions, so it gives the system operator some flexibility with this result. The tool also identifies the grid elements which are constraining the grid for further power injection, which can be targeted for reinforcement. So, regarding the methodology, it is a two-step approach. We start with the non-simultaneous NCA, whose results will then feed the simultaneous NCA. Regarding the non-simultaneous NCA, we start by iteratively increasing power injection in one node of the grid, one node at a time, or one bus. We then increase this by steps until we reach a system limit, either a congestion or a loading limit, or under or over voltage has been reached. Once this happens, we go back to the previous step, reduce the step increase by half, and we keep repeating the process until the step size reaches a negligible amount, at which point we define that this is the maximum power for that node. And we do this for each of the candidate buses separately, so hence the name non-simultaneous. These results will then be boundaries for the simultaneous NCA, which will will solve the NCA problem, nodal capacity allocation, but simultaneously. So for every bus or every candidate bus that we want for that particular grid. For this, we use a generic algorithm. In this case, the fitness of the problem that we want to optimize is the sum of all injected power. So again, we want to maximize the total power injection in the network. And for this, we will find solutions for the maximum capacity that each node has to absorb this power. So the genes in this case will be the injected power in each bus, and the chromosome will be a solution, and the population will be a set of solutions. So each run of the generic algorithm will give us a set of solutions, and to increase this set of solutions, we run the generic algorithm several times. And this is how the result will be a general sense of how much margin each node has for further power increase, rather than just one solution. This is the optimal, you should do this. So, the test case and results. On the left side, we see the grid model that we used. This is a low voltage distribution network from the DSO CUERVA. And on the right, here is the scenario selection, the scenario that we selected to run the Nodal capacity allocation tool. So we have a history of 4 years of consumption for this network. Here we have the total load of that network, and we selected the worst case scenario for power injection, which is a low load scenario. We can interpret this in simple terms. If we are trying to assess limits regarding power injection, we need low load, because if we have more load, that load will itself absorb the power injection, and it will be easier for the network to absorb that injection. And we want to see the worst case scenario, which if it's the maximum power injection for that worst case scenario, it will also work for all the other operating scenarios. So, regarding the results themselves, as I said before, we don't have one solution for each candidate bus. We have a set of solutions which are represented by each of these box plots. We can notice that some of the boxes are larger and the others are smaller, which means that each bus either has, or some buses have a wide range of possible and optimal solutions, or near optimal solutions, and the others don't. So in every run of the genetic algorithm, they have around the same amount of power, which means that some buses are more independent, so to speak, in the terms of power injection with relation to what's happening with other buses, while others, which have a wider range of possible solutions, are more constrained to what's happening on the other buses. Sometimes the algorithm favored that bus in detriment of others, and vice versa, while maintaining the optimality of the solution as a whole. This question of bus independence is something we explored after we wrote the paper in the project, in the steps ahead of the project, so I won't prolong myself too much in this, but the range of possible solutions is an indication of the independence that each bus has. Here we have the fitness of all of the solutions. So here, just to show you that not all the solutions have the same fitness. They're not all optimals, otherwise it would just be 1 point. But the range of possible solutions fitness doesn't vary that much. And here we have some results regarding line loadings for compound solutions. So, for example, taking the maximums of these boxes, the means and the medians, we obtain these line loadings, and here we tried to see if we could make a compound solution that would be suitable from all of the other individual solutions. And we see that for some it works. For the maximum, obviously, we have a lot of overloads. For the median, we have one perhaps overload. And for the mean scenarios, some of the loads are near 100% line load. And here is another output of the tool, which is the grid reinforcement list. So for each of the buses, we have the corresponding grid element that is constraining further power injection in that bus. So in theory, if we inject more power in bus number 2, it will be line 1 that will be overloaded, or it will be the first to be overloaded. So to conclude, we developed a novel method for system-wide nodal capacity allocation for distribution networks. It provides several different solutions, so giving DSOs flexibility on how to manage the installation of new energy sources. It provides the sets of the elements that are limiting and constraining the grid for further power injection. This tool was validated on the low voltage grid, and this method is able to cope with the non-convexity of the problem effectively. With regards to future work, it would mostly be the parallelization of the method, so we could run the tool faster for more iterations, so we could have an even higher diversity of results, and the incorporation of this tool with another tool which would include the possibility of storage installation to see if we could improve even further the nodal capacity of the buses. Thank you very much.